Good morning, plucky provers. The next two videos are going to cover two really important tactics that we're going to use to reason about data types. So I'm going to break this section up into two. We're going to do one video on a tactic called injection and one video on a tactic called discriminate. Both of these tactics are about reasoning about the way that constructors of data types work. So we'll start with injection. Let's get started. There's two principles we care about for constructors in Coq. So they have two properties. They're injective. Now this is a word I defined on day 11. Maybe you don't remember what it means. I'll go over it. And also they are disjoint. Let's see an example. So let's consider the naturals. Injectivity says, look, every constructor produces a unique thing. So if successor of n is equal to successor of m, then it must hold that n equals m. Another way to say this is that the constructor S is injective. So if you remember the definition of injective, uh, it was something like this. Yeah, if I can get my fingers in the right spot on the keyboard. So x, y are types. F is a function from x to y. Here's the proposition of injectivity for all a, b. F of a equals f of b implies a equals b. This is the definition of injectivity. And every single constructor in Coq is injective, right? If the successor of two numbers is equal, if s of n equals s of m, right, then it must be the case that those numbers are equal, right? If I have the number 2 and I take the successor of it, and then somewhere else I compute the number 2 and I take the successor of it, both of those are going to get me to 3. You're going to get the same thing. Okay, that's injectivity. That's what today's video will be about. I'm going to define disjointness, even though the actual video about disjointness will be the next one. So disjointness says every destructor is distinct, right? They produce different things. 0, O, is not equal to successor of n for any n. There's no, it's not like you get to 150 and then you say, the successor is that's the same as O. That's the same as 0. Right? Every constructor is disjoint. No node is equal to any empty. No cons is equal to any nil. Right? Going back to binary, T2P and T2P1 are never going to be equal for any arguments. Now, thinking back to binary, you might be confused by that. It's like, well, didn't we see that T2P BZ is the same as BZ? And say, well, it's not that they're the same. They're different constructors. We interpreted them the same. Keeping track of this distinction is going to be important. Okay, with those generalities out of the way, let's look at how we talk about injectivity in Coq. Okay, so let's first prove that successor is injective. So here's the definition of injective sort of generally. So here, let's prove that particularly S is injective. Okay. For all natural numbers n and m, successor of n equals successor of m implies n equals m. Okay, let n and m be given such that S of n equals S of m. Well, let's do this without any fancy new tactics. We could say, well, look, the predecessor function should actually help us a lot. So let's say that n equals pred Sn. Right, so this is true. N is going to be equal to the predecessor of successor of n. Okay, great. Now can we prove this? Sure. This is just by reflexivity. Okay, so this gives us a hook now. So now we could say something like, well, let's rewrite by h2. Let's rewrite by h1 to change that s of n to s of m in the goal. Right? So this is going to change this. And then if we simplify, you can see that, oh, well, this pred and this s are going to kind of collide and break up. Okay, so great. You can prove on your own that successor is injective. Now, to do it, we had to sort of see this funny trick using predecessor, which kind of like captured that idea for us a little bit. Now, it turns out that you could do this for any data type. You could define something like predecessor that did the right thing here and prove it sort of in general. It would be tedious and you'd have to find these lemmas and so on. Now, it turns out Coq can sort of reason more natively about this. So there's just a tactic that does it. So let's see what happens. Okay, so let nm and h be given. Okay, S of n equals S of m. And now there's a tactic injection h, which says that, hey, h is an equality. That's when you use injection. H is an equality between two things that are constructed with data types, right? So we can see, oh, there's necessarily some data type structure here. And then here I'm going to give a pattern. So the exact patterns you give here are kind of hard to figure out. Let's look at what this proof does, and then we'll see what happens if you leave the pattern out. Because the way that you're going to do it is you'll do it without the pattern at first, and then figure out what pattern you need to write. So when we say injection H is HNM, that just turns, like this is exactly the principle of injectivity. It turned S of n equals S of m directly into n equals m. Fantastic. So then we just apply it. What happens if we don't write this as pattern? Look closely at our goal. Watch what happens. So there we kept, without the as, we kept H, right? H hung around. And then we got a new implication here. So now we could say intros HNM. Okay, so if you're not sure how to use these as, what you're going to do for the as, you have to name every equality that injection is going to find for you. Now, for natural numbers, if it's just two things, you should get just one equality. And when we start doing proofs about lists and so on, that'll be the next one, you'll see that injection can do more. It can derive multiple equations at once. You can have a bunch of stuff going on. So at first, you're not going to be able to guess what those equations are because you won't have a feel for it yet. So then what you want to do is just do injection, see how many things you get, intros them, and then that tells you what to do here. Right? You can just convert the intros in that way, and then you'll be good to go. Okay. Hopefully that makes sense. Maybe watch it over if it doesn't again. That basically the injection tactic witnesses this principle of injectivity for constructors that I asserted is true in Coq. Let's look at another example. Okay, for all natural numbers n, m, o, the list n, m is equal to the list o, o implies that n equals m. You believe that? I believe that. I mean, look, just working positionally, n then has to be equal to o. M then has to be equal to O. And then, okay, let's get real. I'm feeling like a transitivity kind of mood, right? You get people getting transitivity vibes. Let's see how it works. So, intros NMOH. Now, injectivity says that, well, look, cons of two things is going to be equal only if the parts are equal. The same way that successor of two things are equal only if the parts are equal. So we should be able to use injectivity to conclude that informal reasoning I said that n has to be equal to O and m has to be equal to O. Let's see what happens when I just say injection H. Okay, so what did we learn? We learned that m has to be equal to O and n has to be equal to O. Interesting. Okay, so that means I could do something like this. HMO, HNO. And then we could say rewrite HMO, rewrite HNO, reflexivity. Cool. That works. Now, what if we want to do this with an as tactic? You might think, so I said, oh, just convert the intros to an as. But look at what happened. If I kept the same order as the intros, HMO is actually the equation for n, and HNO is actually the equation for m. So this is annoying. Basically, in the as pattern, the list order is reversed from what you would do from intros. So I'm just going to swap the order here, and now the names match up. If that was confusing, like, I think it's actually not that big a deal. What it just means is that if you're not careful using it, the as for injection, you could end up having funnily named things if you're not paying much attention. That's all. So just be careful. So I said also, oh, I'm getting transitivity vibes here. We could prove this with transeq. Right, and then we'd have to prove the list n is equal to the list O, but it ends up actually not saving us any trouble because our equations here are between n and O, not the list n and the list O. I'll finish this proof just to make it clear. So first sub goal, right, whichever proof you want to do here, it's really up to you. I like this one. Okay, so your homework here is going to be about this sort of fancy chain of reasoning. If you get stuck on this, there's a lot of letters, there's a lot of conses. It's actually genuinely hard to keep track of. My advice to you: work it out on paper. Just like get a paper and just sort of like what are x and y and l, what's z, what's j, what has to be equal to what. Convince yourself of the reason why, and then see what order of rewrites or whatever you need to get in cock in order to get the cock to believe you. So you're going to need injection here. Different proofs will use injection different numbers of times, right? So there's a way to do this with just one, and there's a way to do this with two. Any more than that, you've probably gone off the rail. Okay, next video I'll be talking about disjointness. Talk to you soon.